And now in this lecture we'll answer on two questions. In the first question we'll find out the radius of this circle that is inscribed by triangle ABC. In the second question we'll find out the area of this rectangle ABCD that blocks this circle. So we'll start with the first question. In the drawing we have triangle ABC. Side BC equals to 2 units, angle ABC equals to 60 degrees, angle ACB equals to 75 degrees. Inside the triangle we have a circle, and our mission is to find out the radius of this circle. We'll start with two different methods, so we'll start with the first method. Here we will do a construction from point C. We will draw perpendicular on AB. So this angle is equal to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB as D. So we created here triangle BDC, a right triangle. So I'll copy the right triangle BDC in a new page, and we will analyze triangle BDC. Okay. So this is the right triangle BDC with the copy from the original drawing. Angle CBD equals to 60 degrees. This angle is a right angle, and side BC equals to 2 units. We know that the sum of the angles in any triangle is equal to 180 degrees, so which angles we have in triangle DBC? We have this angle that is equal to 90 degrees, plus this angle that is equal to 60 degrees, plus this angle that we will define as angle X. In total, the sum of those three angles must be equal to 180 degrees. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. So here 90 degrees plus 60 degrees is 150 degrees, and 150 degrees plus x must be equal to 180 degrees. Here we subtract 150 degrees from this equation, and we get that the missing angle x, is equal to 30 degrees. So this angle x equals to 30 degrees. we'll continue to focus on the right triangle, triangle DBC. In the right triangle, triangle DBC, sinus 30 degrees is equal to dB over BC. Okay, so sinus 30 degrees equals to dB over BC. BC is 2 units, so we substitute BC by 2, and sinus 30 degrees equals to 1/2, so we substitute sinus 30 degrees by 1/2, and we get that 1/2 equals to dB over 2. Here we will multiply this equation by 2, and we get that dB equals to 1. So I found out that dB equals to 1, so I can write here that dB equals to 1 unit. We'll continue to focus on the right triangle, triangle DBC. In the right triangle, triangle DBC, cosine 30 degrees equals to DC over BC. Okay, cosine 30 degrees equals to DC over BC. So cosine 30 degrees equals to DC over BC. BC is 2, so I'll substitute BC by 2. And we also know that cosine 30 degrees is square root of 3 over 2, so we'll substitute cosine 30 degrees by square root of 3 over 2. So square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2, and we get that DC is equal to square root of 3 units. So here we found out that DC equals to square root of 3 units. In the next step, we will find out the size of angle ACB. Angle, first of all, we have already found out that this angle equals to 30 degrees. So the size of angle DCB, this angle, is equal to angle ACB, the big angle that is equal to 75 degrees, minus angle BCD that is equal to 30 degrees. So 75 degrees minus 30 degrees is 45 degrees. So I found out that this angle equals to 45 degrees. So in the next step, I will copy triangle ADC in a new page, and we will analyze triangle ADC. This triangle, triangle ADC. DC equals to square root of 3 units. Angle ACD equals to 45 degrees. This angle equals to 90 degrees. It is a right triangle. So this is the right triangle, triangle ADC that I copied from the original drawing. In triangle ADC, the sum of the angles is equal to 180 degrees. So which angles we have at triangle ADC? We have this angle that is equal to 90 degrees. plus this angle that is equal to 45 degrees plus the missing angle that we define as angle X. In total, the sum of those three angles must be equal to 180 degrees. $90 degrees plus 45 degrees is 135 degrees plus X must be equal to 180 degrees. Here we subtract 135 degrees from this equation and we'll get that the missing angle, angle X, equals to 180 degrees minus 135 degrees, it is equal to 45 degrees. So here, therefore actually triangle ADC is a right triangle and also an isosceles triangle. Okay, so, and we have the rule that in front of equal angles in the triangle there are equal sides. So in front of this angle we have side AD, while in front of this angle we have side DC. And those two sides must be equal to each other. Those two sides must be equal to each other because they are located in front of equal angles. But we have already found out that DC equals to square root of 3 units. So we can write down that DC equals to square root of 3 units. And from this equation, AD equals to DC equals to square root of 3 units. We will derive that AD is also equals to square root of 3 units. Here AD equals to square root of 3 units. In order, from here we found out that AD equals to square root of 3 units. So in order to find out the hypotenuse of this right and isosceles triangle, triangle ADC, we will implement the Pythagoras theorem on this right triangle and the isosceles triangle, triangle ADC. So here by PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC and the square of the hypotenuse is AC square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AD square plus DC square. Okay. So AC square must be equal to AD square. AD equals to square root of 3. Therefore, AD square is square root of 3 square, that is 3. Plus DC square. DC equals to square root of 3, therefore DC square is square root of 3 square, that is 3. So in conclusion, we found out that AC square equals to 3 plus 3, that is 6. Here we take a root out of this equation, equation number 1, and we get that AC equals to the square root of 6 units. AC equals to square root of 6 units. Yeah. AC equals to square root of 6 units. Okay, so here we found out the lengths of all the sides of triangle ABC. Now we can find out the radius of this circle that is described by triangle ABC according to a new formula. Here a circle that is described by triangle ABC that could be any triangle. The radius of this circle is R, And according to the new formula, the radius of this circle that is described by triangle ABC will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. Okay, so we'll implement the new rule in our drawing. So here, according to the new formula, the radius of this circle that is described by triangle ABC, so the radius of this circle will be defined as R. It will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. And the semi-perimeter of any triangle is equal to the perimeter over 2. Okay, so here the radius of this circle is equal to the area of triangle ABC over the semi-perimeter of triangle ABC. So the area of triangle ABC is equal, this is the sign of the area, the squared brackets, it is equal to the base of the triangle times the height to the base over 2. This is the area of any triangle, and especially of triangle ABC. So the area of triangle ABC will be equal to, here we'll take the base as AB, so it is AB times the height to the base. The height to the base must create 90 degrees with the base, so DC creates 90 degrees with the base, so the height is DC over 2. I'll repeat again, the area of triangle ABC equals to AB, that is the base, times DC, that is the height of the base, over 2. So the area of triangle ABC will be equal to AB. AB is 1 plus square root of 3 units. 1 plus square root of 3 units times DC. DC equals to square root of 3 units. Square root of 3 units over 2. Okay. So here we'll open the brackets on this side of the equation, and we'll get that the area of triangle ABC equals to 1 times square root of 3 square root of 3 square root of 3 times square root of 3 is 3 over 2. Square root of 3 is 1.732 plus 3 over 2, of course, over 2. 3 plus 1.732 is 4.732 over 2. That is equal to 2.366. So we found out that the area of triangle ABC is equal to 2.366 square units. In the next step, we find out the semi-perimeter of triangle ABC. So I already mentioned the semi-perimeter of any triangle equals to the perimeter over 2, and the perimeter of triangle ABC equals to AB plus AC plus BC. And if we divide the perimeter by 2, we get the semi-perimeter. So we divide it by 2. So AB equals to 1 plus square root of 3 units. AC equals to square root of 6 units. And BC equals to 2. Okay, all divided by 2. So we get here that the semi-perimeter of triangle ABC S equals to 1 plus 2 is 3. 3 plus square root of 6 plus square root of 3 over 2, it is equal to the semi-perimeter of triangle ABC. And here we get that the area of triangle and the semi-perimeter of triangle ABC equals to 4.59 units. And here we know that the radius of the circle that is inscribed by triangle ABC R equals to the area of triangle ABC over the semi-perimeter of triangle ABC. The area of triangle ABC equals to, check it, actually the area of triangle ABC is equal to square root of 6 plus square root of 3 plus 3 over 2. So the semi-perimeter of triangle ABC equals to 3.59. Here the semi-perimeter equals to 3.59. The area is equal to 2.366 square units, and 2.366 square units over 3.59 units, it is equal to 0.65 89 units. Okay, I repeat again, the radius of the circle that is inscribed by triangle ABC, the radius of this circle is equal to 0.6589 units. So I finished with the first method. In the next step, I will present to you the second method to find out the radius of this circle that is inscribed by triangle ABC. In the second method, we will define the center of the circle as point O. We will define the point of tendency of tangent BC with this circle as D. We will join points O and D together by a straight line. Here, point O is the center of the circle, point D is a point on the circle itself. Therefore, OD is the radius of the circle, so we define the radius of the circle as R. So OD equals to R. And we have the radius OD that is drawn to point D, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. Okay, here we have, according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here the radius OM, it is drawn to point M, that is the point of tendency of tangent AB with this circle. Therefore, according to rule number 1, tangent AB will be perpendicular to the radius MO. That is to say, this angle will be equal to 90 degrees, and this angle also will be equal to 90 degrees, according to this rule number 1. Here, the radius OD is drawn to point D, that is the point of tendency. Therefore, tangent BC will be perpendicular to the radius DO. If this is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule number 1. In the next step, we join points O and C together by a straight line. We join points B and O together by a straight line. We define the point of tendency of tangent AB with this circle as E. We define the point of tendency of tangent AC with this circle as F. Here we join points O and D together by a straight line. So here point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of the circle that is equal to R. Likewise, here we join points O and F together by a straight line. And again, here point O is the center of the circle, point F is the point of the circle itself, therefore OF is the radius of the circle that is equal to R. And here E is the point of tendency of tangent AB in the circle, and we have the radius OE that is drawn to the point of tendency, that is to say it is drawn to point E. Therefore the radius AB will be perpendicular, therefore the radius, the tangent AB will be perpendicular to the radius EO. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Likewise, we have the radius OF that is drawn to the point of tendency, that is to say it is drawn to point F, that is the point of tendency of tangent AC with this circle. Therefore, tangent AC will be perpendicular to the radius FO. That is to say this angle will be equal to 90 degrees according to rule number 1, and this angle will be also equal to 90 degrees according to the same rule. So here we will prove that the green triangle POF is congruent to the orange triangle BEO. But before that, I will present to you rule number 2 also. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So here we have the common standpoint point P. From the common standpoint point P, we have tangent PA and tangent PB to the circle. According to 1/2, the lengths of those two tangents are equal to each other. This is to say PA equals to PB. So you can implement rule number 2 in our drawing. Why? Because in our drawing, we have the common standpoint point B. From the common standpoint point B, we have two tangents to the circle. Tangent BD and tangent BE. And according to rule number 2, they are equal to each other. That is to say here, BD is equal to BE. Likewise, we'll focus on point C. In the common standpoint point C, from the common standpoint point C, we have two tangents to this circle. We have tangent CD and tangent CF, and those two tangents are equal to each other according to rule number 2. So CD is equal to CF. Okay? So here we'll prove that the green triangle is congruent to the orange triangle. Okay, so why the green triangle is congruent to the orange triangle? We prove that the green triangle, that is actually triangle OBD, is congruent to the orange triangle, that is triangle OEB. So, why those two triangles congruent to each other? First of all, we just right now found out that side BD of the green triangle is equal to side BE in the orange triangle according to rule number 2. Okay. In addition, side DO of the green triangle is equal to side OE of the orange triangle. Why? Because they are both the radii of the circle, therefore they are equal to each other. And finally, side OB is a common side that belongs to both triangles, so OB equals to itself. OB equals to OB is a common side that belongs to both triangles. So actually, we proved that the two triangles can go into each other according to side rule. Okay, I write it down. Triangle, the green triangle, triangle OBE, can go into the orange triangle, triangle OEB, according to side rule. And from the fact that the two triangles can go into each other, we derive that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles must be also equal to each other. So you can write down that angle OBD of the green triangle is equal to angle OBE of the orange triangle. Okay. Repeat again. Angle OBD equals to angle OBE according to the rule that corresponding angles in congruent triangles are equal to each other. So if we define angle OBE as alpha, then from this equation we conclude that angle OBD is also equal to alpha. Angle OBD equals to alpha. So we actually found out that both those two angles are equal to alpha according to our definition, and the sum of those two angles is alpha plus alpha. And alpha plus alpha is equal to 60 degrees according to what is given as the question. Alpha plus alpha equals to 60 degrees. Alpha plus alpha is 2 alpha. 2 alpha equals to 60 degrees. We divide this equation by 2 and we get that alpha equals to 30 degrees. Okay, here angle alpha equals to 30 degrees. Here angle alpha equals to 30 degrees. And here angle alpha equals to 30 degrees. Those two triangles actually can go into each other according to side rule. We will not repeat on the same process, it is exactly the same like here. And from the fact that those two triangles can go into each other, we conclude that those two angles are equal to each other. That is to say, angle OCD is equal to this angle. It is actually angle OCF. Okay, angle OCD equals to angle OCF. So if we define angle OCF as theta, and this angle equals to theta, then from this equation, angle OCD equals to angle OCF equals to theta, we derive that angle OCD is also equals to theta. So those two angles, here, those two angles, they are both equal to theta, and the sum of those two angles is theta plus theta. Theta plus theta equals to 75 degrees according to what is given as the question. So theta plus theta equals to 75 degrees. Theta plus theta is 2 theta. 2 theta equals to 75 degrees. We divide this equation by 2 and we get that theta equals to 37.5 degrees. Angle theta equals to 37.5 degrees. Here we can find out that angle theta equals to 37.5 degrees. And here also angle theta equals to 37.5 degrees. According to God, the corresponding angles in congruent triangles are equal to each other. In the next step, we'll focus on the green triangle, triangle OBD. In the green triangle, triangle OBD, tangents 30 degrees equals to OD over BD. Okay, tangents 30 degrees equals to OD over BD. Tangents 30 degrees equals to OD over BD. OD equals to R. We substitute OD by R, so it is R over BD. So here we multiply tangents 30 degrees by BD, then we divide it by tangents 30 degrees. We multiply this equation by BD and then we divide it by tangents 30 degrees and we get that BD equals to R over tangents 30 degrees. Okay, we found out the value of BD. In the next step, we will focus on the yellow triangle, triangle ODC. In the right, yellow triangle, triangle ODC. We know that triangle on DC. Here tangents 37.5 degrees is equal to OD over DC. Repeat again. Tangent 37.5 degrees equals to OD over DC. So here OD equals to R, so we substitute OD by R, so it is R over DC. Tangent 37.5 degrees equals to R over DC. Here, we multiply this equation by DC, and then we divide it by tangent 37.5 degrees, and we get that DC is equal to R over tangent 37.5 degrees. Okay. So we actually found out the values of DC and BD. And it is very clear from the drawing that the length of side BC it is equal to BD plus DC. BD plus DC. Okay, DC equals to BD plus DC. It is very simple, very clear from the drawing. So DC equals to BD. We already found out that BD equals to R over tangent 30 degrees plus DC. DC equals to R over tangent 37.5 degrees so here we take R as a common factor out of those two expressions, and we get that it's actually BC. Okay, I made a mistake here. It is BC. It is very clear from the drawing that BC equals to BD plus DC. Again, BC equals to BD plus DC. Okay, and we already found out the value of BD and DC. So we take R as a common factor, but we also know that BC equals to 2 units, therefore we substitute BC by 2. So 2 equals to, we took R as a common factor, so what is left from R over times 30 degrees after we took R as after we took from it R as a common factor? What is left is actually 1 over times 30 degrees. What is left from R over times 37.5 degrees after we took from it R as a common factor? What is left? Actually 1 over tangent 75.5 degrees. Okay. We calculate the values of this expression, we add them together, and this way we find out the radius that we are looking for. So here 1 over times 30 degrees equals to 1.732, and 1 over times 37.5 degrees equals to 1.303. Okay, so 2 equals to R, and 1.732 plus 1.303, it is equal to 1.303 3.035. So here we divide this equation by 3.035. And we'll get that the radius equals to 2 over 3.035, 2 over 3.035, is equal to 0.6589 units. So actually in both methods we found out that the radius of this circle that is inscribed by triangle ABC equals to 0.6589 units. So we actually finished with the first method. In the next step, we finished with question 1. So in the next step, I will present to you the second method, and we will solve. In this next step, I will present to you the second question, and we will solve the second question in two different methods. So in the drawing we have rectangle ABCD. Inside rectangle ABCD we have a circle chord PS equals to 6 units, line segment SQ equals to 5 units, and our mission is to find out the area of this rectangle ABCD. Okay, so first of all we will define the center of the circle as O. Point P is the point of tendency of tangent BC with this circle. P is the point of tendency of tangent BC with the circle. So we join points P and O together by straight line. So here, point O is the center of the circle. Point P is a point on the circle itself. Therefore, OP is the radius of the circle. So we define the radius of the circle as R. OP equals to R. We know that all the angles inside a rectangle are right angles. So here, all those angles are right angles. ABCD is a rectangle, of course. And we define side AB as A. We define the length side BC of rectangle ABCD as B. And it is very easy to prove that BC is also the diameter of the circle, so I write it down. BC is the diameter of the circle. So actually, we know that BC equals to B, so B is the diameter of the circle. If the diameter of the circle is B, the radius equals to half of it, that is to say R equals to B over 2. R equals to B over 2. So here we have the radius OP that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. We define the point of tendency of tangent DC with this circle as point F. Again, point F is the point of tendency of tangent DC with this circle. We join points O and F together by a straight line. Here this is actually point F. This is the point of tendency of tangent DC with this circle. So here again we have point O is the center of the circle. Point F is the point of the circle itself. Therefore OF is the radius of the circle. And we have the radius OF that is drawn to the point of tendency, that is to say it is drawn to point F. Therefore, according to rule number 1, this angle will be equal to 90 degrees and this angle also equals to 90 degrees according to rule number 1. We actually found out that in quadrilateral OPFC, again in this quadrilateral OPFC, we have 1, 2, 3 right angles. So therefore the fourth angle must be also equal to 90 degrees in order to complete the sum of the angles in quadrilateral OPFC to 360 degrees. This angle must be equal to 90 degrees. Okay. So here I will present to you a new rule that is actually rule number 4. According to rule number 4, the perpendicular from the center of a circle to a chord bisects the chord. Here the perpendicular O is the center of the circle. So OM is the perpendicular from the center of the circle to chord CD, and according to this rule number 4, the perpendicular OM bisects chord CD. This is to say CM equals to MD. Okay, so here we implement rule number 4 in our drawings. We will draw from the center of the circle, that is to say from point O, perpendicular on chord SP. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. Okay, we define the touching point of the perpendicular from point O and SP is M. According to rule number 4, the perpendicular OM bisects chord SP. That is to say, according to rule number 4, SM equals to MP. SM equals to MP, according to rule number 4. So, if we define MP as X, here MP equals to X according to our definition, from this equation SM equals to MP equals to X, we derive that actually define there MP as X. Okay, so from this equation SM equals to MP as X, we derive that SM is also equals to X. SM is also equals to X, here SM equals to X. So SP equals to X plus X. Here SP equals to X plus X. And SP equals to 6 units according to what is given as the equation. Here SP equals to 6 units. So here from this equation S6 equals to SP equals to X plus X, we derive that 6 equals to X plus X. So 6 equals to X plus X, that is 2X. We divide this equation by 2 and we get that X equals to 3 units. So I found out that X equals to 3 units. Here X equals to 3 units and here also X equals to 3 units. Okay. In the next step, from point Q, this point Q, we go perpendicular on BC. Okay, repeat again, from point Q, we go perpendicular on BC. So actually, this angle equals to 90 degrees according to our construction, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and BC as L. We define the intersection point of the perpendicular QL and the radius QF as T. Actually, by drawing this perpendicular, we created here quadrilateral QPTL. And inside quadrilateral QPTL, we have 1, 2, 3 right angles. And any quadrilateral that has 3 right angles, the fourth angle must be also equal to 90 degrees, so I already mentioned. Okay, this angle equals to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So, quadrilateral QPTL has 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we will relate to quadrilateral QPTL as a rectangle. Why? Because it has 4 right angles. We'll repeat again. Quadrilateral QPTL is a rectangle. But we also know that the opposite sides of a rectangle are parallel to each other. Here, so therefore OP is parallel to TL. OP is parallel to TL according to the rule that the opposite sides of a rectangle are parallel to each other. But here TL is part of the perpendicular QL. Okay? TL is part of the perpendicular QL. QL as a perpendicular, it is absolutely a straight line. Okay, so we can write down that QL is a straight line because it is a perpendicular. QL is a straight line. Again, QL as a perpendicular is a straight line. And we know that the straight line QL consists of this line segment TL. So TL is part of the straight line QL. And TL, that is a part of the straight line QL, is parallel to OP. And we have the rule that if a part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the straight line, to another straight line. Again, if the straight line TL is parallel to OP, it means that QL itself, the straight line QL, must be also parallel to OP. Why? Because if part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Okay, therefore QL must be parallel to OP. QL must be parallel to OP. And we also have here rule number 9. According to rule number 9, alternating angles between parallel lines are equal to each other. Line A is parallel to line B. So those two pink angles are defined as alternating angles, and they are located between the parallel lines A and B, therefore they are equal to each other. You can implement rule number 9 in our drawing. Why? Because in our drawing we have the parallel lines OP and QL, and those two angles are defined as alternating angles, and they are located between the parallel lines OP and QL, therefore they are equal to each other according to rule number 9. So I write it down. Angle OPQ is equal to this angle, that is actually angle LQP. repeat again, angle OPQ equals to angle LQP. Why? Because those two alternating angles that are located between parallel lines, therefore they are equal to each other. So if we define angle LQP as theta, here this angle equals to theta according to our definition, then from this equation angle OPQ equals to angle LQP equals to theta, we will derive that angle OPQ is also equals to theta. Okay, here this angle equals to theta. Okay, in the next step we'll focus on quadrilateral QDLC again. We'll focus on quadrilateral QDLC, this quadrilateral. In quadrilateral QDCL, we have 1, 2, 3 right angles. Again, in quadrilateral QDCL, we have 1, 2, 3 right angles. Any quadrilateral that has 3 right angles, the fourth angle must be also equal to 90 degrees. So this angle is equal to 90 degrees. So actually, quadrilateral QDCL has 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate quadrilateral QDCL as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. So side QL must be equal to side DC. Okay? But here we also know that AB equals to A according to our definition. Here QL equals to DC according to the rule that the opposite sides of a rectangle are equal to each other. QL equals to DC. Okay, QL equals to DC. But we also know that ABCD is a rectangle, and the opposite sides of rectangle ABCD are also equal to each other. That is to say, AB equals to DC. And here, AB equals to DC, or DC equals to AB. And from this equation, QL equals to DC equals to AB, we will derive that QL is also equals to AB. QL equals to AB, but QL also equals to A according to our definition. Here, AB equals to A according to our definition. AB equals to A according to our definition. And from this equation, QL equals to AB equals to A, we will derive that QL is also equals to A. QL is also equals to A. Here we can write down that QL equals to A. Okay, so in the next step, we'll focus on the green right triangle, triangle OMP. So I'll copy the green right triangle, triangle OMP in a new page, and we'll analyze triangle OMP. Okay. Angle OMP equals to 90 degrees, according to rule number 4. This angle equals to theta, according to rule number 9. we already found out that MP equals to 3 units, and the hypotenuse OP equals to B over 2. So actually, this is the right triangle OMP that they copied from the original drawing. And the right triangle OMP, cosine theta equals to MP over OP. Again, cosine theta equals to MP over OP. I write it down, cosine theta equals to MP over OP. MP equals to 3 units, so we substitute MP by 3. And OP equals to B over 2, so we substitute OP by B over 2. Here 2 moves to the numerator, and 2 times 3 is 6. And B moves to the denominator, so it is 6 over B. So in conclusion, we found out that according to equation number 1, cosine theta equals to 6 over B. In the next step, we'll focus on the big right triangle QPL. On the big right triangle QPL, what is the value of cosine theta? Cosine theta equals to QL over QP. Repeat again. In the big right triangle QPL, cosine theta equals to QL over QP. We have already found out that QL equals to A, so we substitute QL by A. What is the value of QP? From the drawing it is very easy to see that QP equals to 5 plus 6. QP equals to 5 plus 6, that is 11. So we substitute QP by 11. So in conclusion, we found out that cosine theta, according to equation number 2, it is equal to A over 11. Repeat again, cosine theta according to equation number 2 equals to A over 11, and cosine theta according to equation number 1 equals to 6 over B. So we have two different expressions for cosine theta, therefore we'll create equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. So cosine theta according to equation number 1 equals to 6 over B, and it must be equal to cosine theta according to equation number 2, that is equal to A over 11. So in conclusion, we found out that 6 over B equals to A over 11 according to equation number 3. So here we cross multiply this equation number 3, and we get that here according to equation number 3, A times B equals to 6 times 11, that is 66. So in conclusion, we found out that A times B equals to 66. And what is the area of rectangle ABCD? The area of rectangle ABCD is equal to the length of the rectangle times the width. The length is AB and the width is BC. So the area of rectangle ABCD equals to AB times BC. According to our definition, AB equals to A and BC equals to B. So the area of triangle ABCD is A times B, and we already found out that according to equation number 3, AB equals to 66. So in conclusion, we found out that the area of triangle ABCD is equal to 66 square units. Okay, so we finished with the first method. In the next step I present to you how to find out the area of this rectangle ABCD according to the second method. In the second method, we define the center of the circle as point O. All the angles inside the rectangle are right angles. So here, this angle equals to 90 degrees. This angle also equals to 90 degrees. This angle equals to 90 degrees, and this angle also equals to 90 degrees. We define AB as A and BC as B, as we did in the first method. I already mentioned that BC is also the diameter of the circle, so I write it down. So we join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle that we define as R. If the diameter of the circle equals to B, it means that the radius must be equal to half of it, that is to say R equals to B over 2. And we already found out in the first method that according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. We'll extend the radius OP until it touches side AD of rectangle ABCD, until it intersects with side AD of rectangle ABCD. We define the intersection point of the extended OP and AD as F. So here we have quadrilateral ABFP. Inside quadrilateral ABFP we have 1, 2, 3 rectangles, and then quadrilateral that has 3 right angles. The fourth angle must be also a right angle. Okay. Likewise, if you focus on quadrilateral FPDC, we have 1, 2, 3 right angles. And according to the same rule, this angle must be also equal to 90 degrees. Okay. So we define the touching point of the extended radius OP in the circle is point M. MP is a chord in the circle, but what definition called MP as? What other definition called MP as? Chord MP passes for point O, that is the center of the circle, and any chord that passes for the center of the circle must be the diameter of the circle. So here MP is the diameter of the circle, and we have already found out that the diameter of the circle equals to B. In the next step, we join points M and S together by a straight line. When joining points M and S by a straight line, we created here peripheral angle MSP. And peripheral angle MSP rests on MP, that is the diameter of the circle. And we actually have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of the circle must be equal to 90 degrees. Here, peripheral angle AMB that rests on AB, that is the diameter of the circle, equals to 90 degrees. We can implement rule number 5 in our drawing. Because in our drawing we have peripheral angle PSM that rests on MP, that is the diameter of the circle. Therefore, according to rule number 5, peripheral angle MSP must be equal to 90 degrees. So this angle MSP equals to 90 degrees according to rule number 5. So here, according to our definition, AB equals to A. We have already found out that ABFP is 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square, so we will relate to quadrilateral ABFP is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side FP from one side, but from the other side AB equals to A and FP equals to AB, therefore FP must be also equal to A. FP equals to A. We define angle MPS as theta. We'll focus on triangle MSP, that is a right triangle, because this angle equals to 90 degrees. This angle equals to theta, so this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle, and especially in triangle MSP. So here we focus on the right triangle, triangle QFP. On the right triangle QFP, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta, exactly for the same reason that this angle equals to 90 degrees minus theta. So in the next step, we'll prove that the right triangle MSP, the right small triangle MSP is similar to the right big triangle QFP. Okay, so we have the right big triangle QFP, and the right green small triangle MSP. So why those two triangles are similar to each other? First of all, we just right now found out that those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So I write it down, angle FQP this angle is equal to this angle that is actually angle SMP. Of angle equals to 90 degrees minus theta, therefore they are equal to each other. I repeat again. Angle FQP in the big triangle, big right triangle equals to angle SMP in the green triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So here angle QFP this angle is equal to this angle that is actually angle MSP. They are both equal to 90 degrees, therefore they are equal to each other. Here angle QFP equals to angle MSP. They are both equal to 90 degrees, therefore they are equal to each other. And finally, this angle is angle theta. That is a common angle. It belongs to both triangles, so angle theta equals to itself. So angle FPQ, that is angle theta, equals to angle MSP, that is also angle theta. So angle theta equals to itself. Angle FPQ equals to angle MSP. They are both angle theta with two different names. So I found out that the big right triangle QFP is the big right triangle QFP is similar. This is the sign of similar to the small right triangle MSP, according to angle similarity rule. And from the fact that the green triangle is similar to the big right triangle, we conclude that the following relationship exists between their sides. We conclude that FP, that is the side of the big right triangle, over SP, that is the side of the small green right triangle, is equal to QP, that is one side of the hypotenuse of the right green triangle, QP, over MP, that is the hypotenuse of the green right small triangle. So here I found out that FP over SP equals to QP over MP. The value of FP is A, according to what we have already found out, so we substitute FP by A over SP. SP equals to 6 units, according to what is given as the question. So we substitute SP by 6, and it is equal to QP. QP, the hypotenuse of the big right triangle, equals to 5 plus 6. Again, QP equals to 5 plus 6, that is 11. So we substitute QP by 11 over MP. MP, that is the hypotenuse of the small right green triangle, equals to B, according to what we have already found out, it is the diameter of the circle. So we substitute MP by B. So in conclusion, we found out that A over 6 equals to 11 over B. Here we cross multiply this equation and we get that A times B equals to 6 times 11, that is 66. AB equals to 66. And we know that the area of rectangle ABCD equals to the length of the rectangle, that is AB, times the width that is BC. AB equals to A according to our definition, and BC also equals BC equals to B according to our definition. So in conclusion, we found out that the area of triangle ABCD equals to AB, but we just right now found out that BC equals to 66. Therefore, that AB equals to 66. So AB equals to 66. So I found out that the area of rectangle ABCD equals to 66 square units. So in both methods we arrived to the same result, that the area of rectangle ABCD, this rectangle, it is equal to 66 square units. So in the next step I will summarize the lecture and start with the first question, of course. So in the drawing we have triangle ABC, and inside triangle ABC we have a circle. The circle is inscribed by triangle ABC. Side BC equals to 2 units, angle ABC equals to 60 degrees, angle ACB equals to 30 degrees. And our mission is to find out the radius of this circle that is inscribed by triangle ABC. In the first method, we did the construction from point C, we drew perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So we created the green triangle, triangle BCD. So I copied the green right triangle, triangle BCD in a new page and analyzed triangle BCD. This is the right triangle BCD that I copied from the original drawing. This angle equals to 90 degrees according to our construction. This angle equals to 60 degrees according to what is given as the question. And this is the missing angle that we define as x. And remember that the sum of the angles in any triangle is equal to 180 degrees. So in triangle BCD, 90 degrees plus 60 degrees plus this angle that is x, in total they must be equal to 180 degrees. 90 degrees plus 60 degrees is 150 degrees, plus x in total must be equal to 180 degrees. We subtracted 150 degrees from this equation and found out that x equals to 30 degrees. Here the missing angle equals to 30 degrees. Okay? So we continue to focus on this right triangle, triangle BDC. In the right triangle, triangle BDC, it is very easy to see that sinus 30 degrees equals to BD over BC. Sinus 30 degrees equals to BD over BC, so sinus 30 degrees equals to BD over BC, but BC is 2, so we substitute BC by 2. And sinus 30 degrees is 1/2, so we substituted sinus 30 degrees by 1/2, and so in conclusion found out that 1/2 equals to BD over 2. Here we multiply this equation by 2 and found out that BD equals to 1. So here we can write down that BD equals to 1 unit. We continue to focus on the right triangle, triangle BDC. In the right triangle, triangle BDC, it is very easy to see that cosine 30 degrees equals to DC over BC. Cosine 30 degrees equals to DC over BC. That is to say cosine 30 degrees equals to DC over BC, but BC is 2, so we substitute BC by 2. I found out that cosine 30 degrees equals to DC over 2. Cosine 30 degrees is square root of 3 over 2, so we substitute cosine 30 degrees by square root of 3 over 2. So in conclusion, we found out that square root of 3 over 2 equals to DC over 2. We multiplied this equation by 2 and we found out that DC equals to square root of 3 units. Here, DC equals to square root of 3 units. Then we found out that the size of this angle equals to the big angle, that is angle ACB, that is equal to 75 degrees, minus the size of this angle, that is equal to 30 degrees. So 75 degrees minus 30 degrees is 45 degrees. So this angle equals to 45 degrees. In the next step I copied triangle ADC, right triangle ADC in a new page, and we analyzed triangle ADC. This is the right triangle ADC that I copied from the original drawing. This angle equals to 90 degrees, this angle equals to 45 degrees. We have already found out that this equals to square root of 3 units. And this is the missing angle. The sum of the angles in this triangle is 180 degrees, that is to say 90 degrees plus 45 degrees plus the size of this angle, that is x. In total, they must be equal to 180 degrees. 90 degrees plus 45 degrees is 135 degrees, so 135 degrees plus x equals to 180 degrees. We subtracted 135 degrees from this equation and we found out that x equals to 180 degrees minus 135 degrees is 45 degrees. So this again equals to 45 degrees. We continue to focus on this right triangle, triangle ADC. In this right triangle ADC, we have those two angles that are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. So in front of this angle, you have side DC. In front of this angle, you have side AD, and those two sides must be equal to each other because of the fact that they are located in front of equal angles. But we have already found out that DC equals to square root of 3. So from this equation, square root of 3 equals to DC equals to AD, we will derive that AD also equals to square root of 3 units. Okay? We continue to focus on the right triangle ADC. We implemented the Pythagoras theorem on the right triangle ADC in order to find out the hypotenuse. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say, AC square equals to AD square plus DC square. AC square equals to AD square. AD is square root of 3, therefore AD square is square root of 3 square, that is 3. Plus DC square. DC is square root of 3, so DC square is square root of 3 square, that is also 3. So in conclusion, we found out that AC square equals to 3 plus 3, that is 6. We took out of this equation, equation number 1, and found out that AC equals to square root of the hypotenuse AC equals to square root of 6 units. Then I presented to you a new formula that will help us to find out the radius of this circle that is inscribed by triangle ABC. The formula states that the radius of the circle that is inscribed by any triangle, it is equal to the area of the triangle over the semi-perimeter of the triangle. And the area of triangle ABC equals to the base times the height over 2. We took the base as AB, the height is DC over 2. AB is 1 plus square root of 3, DC is square root of 3, all divided by 2. We opened the brackets here and we found out that the area of triangle ABC equals to square root of 3 plus 3 over 2, that is equal to 2 times 366. And the semi-perimeter of triangle ABC equals to the perimeter over 2. The perimeter is AB plus AC plus BC. And if we divide it by 2, we get the semi-perimeter. We put the values of AB, AC, and BC inside this formula and found out that the semi-perimeter of triangle ABC equals to 3.59 units. 3.59 units. So here, the radius of the circle that is inscribed by triangle ABC equals to the area of triangle ABC, that is 2.366 per unit over the semi-perimeter, that is 3.59 units. So if we divide the two numbers by each other, we get that the radius of the circle that is inscribed by triangle ABC equals to 0.6589 units. We finished with the first method, then I presented to you how to find out the radius of this circle according to the second method. In the second method, we actually use two rules. Rule number 1, that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. And also rule number 2, that the lengths of two tangents from a common point to a circle are equal. Okay, so created here this Proving all the angles here are equal to here this angle and this angle and this angle also is equal to 90 degrees according to rule number 1, and those are also the radii of the circle, that is r equals to r, and here BE equals to ED according to rule number 2, and DC equals to CF according to rule number 2. Then we proved that the green triangle is congruent to the orange triangle according to side rule. Here, the green triangle OBD is congruent to the orange triangle OED. BD equals to BD equals to BE according to rule number 2. DO equals to OE, they are both the radii of the circle, and OB is the common side that belongs to both triangles. So we proved that the green triangle OBE is the green triangle OBD is congruent to the orange triangle OBE according to side rule. From the fact that those two triangles congruent to each other, we derive that those two angles are equal to each other. So if one angle equals to alpha, then the other angle also must be equal to alpha, because they are equal to each other. So alpha plus alpha must be equal to 60 degrees according to what is given as the question. Alpha plus alpha is 2 alpha, and 2 alpha equals to 60 degrees. We divided this equation by 2 and found out that alpha equals to 30 degrees. So this angle equals to 30 degrees, and this angle that is alpha, it is also equals to 30 degrees. Likewise, according to rule number 2, those two triangles can go into each other according to side rule. Therefore, those two angles must be equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if one angle is theta, then the other angle must be also equal to theta. Okay, and we know that the sum of those two angles, theta plus theta, is equal to 75 degrees according to what is given as the question. So 2 theta equals to 75 degrees. We divided this equation by 2 and found out that theta equals to 37.5 degrees. Angle theta equals to 37.5 degrees. Then we focus on the green triangle OBD. In the green triangle OBD, we know that triangle 30 degrees equals to OD over BD. Again, triangle 30 degrees equals to OD over BD. OD equals to R, so we substitute OD by R, and BD is BD. We multiplied this equation by BD, and then we divided by triangles 30 degrees, and found out that BD equals to R over triangles 30 degrees. Repeated on the same process here. We focused on the yellow triangle ODC. In the yellow triangle ODC, triangles 37.5 degrees equals to OD over DC. Triangles 35 degrees, 37.5 degrees equals to OD over DC. OD is R over DC. Here we multiply this equation by DC and divided it by triangles 37.5 degrees, and found out that DC equals to R over triangles 37.5 degrees. What is the value of BC? BC equals to BD plus DC. BC equals to BD plus DC. BC is B. BC equals to BD plus DC. DC equals to R over triangles 30 degrees. DC equals to R over triangles 37.5 degrees. We took R as a common factor, and we got this expression. 1 over triangles 30 degrees is 1.732. 1 over triangles 37.5 degrees is 1.303. And 1.372 plus 1.303 is 7.035. We divided this equation by 3.035 and found out that R equals to 2 over 3.035, and it is equal to, this expression equals to 0.6589 units. So the radius of this circle equals to 0.6589 units. Okay, we finished with the first question. Then I presented to you the second question, and we solved the second question in two different methods. So here in the drawing we have rectangle ABCD. Inside the rectangle we have a circle chord PS equals to 6 units, line segment SQ equals to 5 units, and our mission is to find out the area of this circle. So we define the center of the circle as point O. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle. We know that all the angles inside the rectangle are right angles, so all the four angles here are right angles. We define AB as A and BC as B. And here, this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. This angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1 also. So we graded here quadrangle OPFC. In quadrangle OPFC we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. Then we implemented here rule number 4 that says that if you draw from the center of the circle perpendicular to the chord, it bisects the perpendicular, it bisects the chord. So here we draw from the center of the circle that is point O, the perpendicular OM. The perpendicular OM bisects chord SP, that is to say SM equals to SM equals to MP according to rule number 4. So if MP equals to X, then SM must be also equal to X. So both of those two line segments are equal to X. And we know that X plus X equals to SP, that is equal to 6. X plus X is 2X, so 2X equals to 6. We divided this equation by 2 and found out that X equals to 3 units. Then from point Q we draw perpendicular on BC, so this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and BC as L. So here we have quadrangle OPTL. In quadrangle OPTL we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So quadrangle OPTL has 4 right angles, therefore it must be at least a rectangle, if not a square. So we relate quadrangle OPTL as a rectangle, and we know that the opposite sides of a rectangle are parallel to each other. That is to say OP is parallel to TL. Here OP is parallel to TL. But TL is part of the perpendicular QL. QL as a perpendicular, it is absolutely a straight line. And if part of a straight line is parallel to the other straight line, then the straight line itself, that is QL, must be also parallel to the other straight line, that is OP. That is to say QL, the straight line QL is parallel to OP. The straight line QL is parallel to OP. And we have here rule number 9 that according to rule number 9, alternating angles between parallel lines are equal to each other. OP is parallel to QL, and those two angles that are defined as alternating angles are located between the parallel lines OP and QL, therefore they are equal to each other. Okay, so here angle OPQ equals to angle LQP according to rule number 9. So if we define angle LQP as theta, then from this equation we derive that angle OPQ is also equal to theta. So both those two angles are equal to theta. Okay, and here we focus on quadrangle QLDC. In quadrangle QLDC we have 1, 2, 3 right angles. Any quadrangle that has 3 right angles, the fourth angle must be also a right angle. Okay, here. So quadrangle QLDC is 4 right angles. Any quadrangle that has 4 right angles must be at least a rectangle, if not a square. So we relate quadrangle QLDC is a rectangle. And in a rectangle, we know that the opposite sides are equal to each other. That is to say, QL equals to DC. QL equals to DC, but ABCD is a rectangle. And the opposite sides of rectangle ABCD must be equal to each other. That is to say, DC equals to AB. So here, DC equals to AB, and from this equation, QL equals to DC equals to AB, we will derive that QL is also equals to AB. QL is also equals to AB, but according to our definition, AB equals to A. So we can write here that AB equals to A, and from this equation, QL equals to AB equals to A, we will derive that QL is also equals to A. QL is also equals to A. Then we focused on the green small right triangle OMP. I copied the green small right triangle OMP in this new page. In the triangle OMP, we know that cosine theta equals to MP over OP. MP equals to 3, OP equals to B over 2. 3 over B over 2 is 6 over B. So according to equation number 1, cosine theta equals to 6 over B. Then we focused on the big right triangle PQL. On the big right triangle PQL, cosine theta equals to QL over QP. Cosine theta equals to QL over QP. QL equals to A, and QP equals to 5 plus 6, that is 11. So in conclusion, cosine theta equals to A over 11. So here we have two different expressions for cosine theta. Therefore, we get the equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. Okay, so cosine theta according to equation number 1 is 6 over B, and it must be equal to cosine theta according to equation number 2, that is A over 11. So according to equation number 3, 6 over B equals to A over 11. We cross multiply this equation number 3, and found out that AB equals to 66. So here, we actually found out that the area of rectangle ABCD is equal to the length times the width. The length is AB, the width is BC. AB equals to A according to our definition, BC also equals to, and BC equals to B according to our definition. So in conclusion, we found out that ABCD equals to AB. But we just right now found out that A times B equals to 66. So here we can write down that AB equals to 66. So in conclusion, we found out that the area of rectangle ABCD equals to 66 square units. Then I presented to you how to find out the area of rectangle ABCD according to the second method. In the second method, here we do it all the things that we already done in the first method. We extended the radius PO until it intersects with side AD of the rectangle at point F. So in rectangle, in quadrangle ABPF, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So quadrangle ABPF is a rectangle. We know that the opposite sides of rectangle are equal to each other. That is to say AB equals to FP. But AB equals to A, therefore FP also equals to A. Okay? And in quadrangle FPDC we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Then we use rule number 5, that's we join points M and S together by a straight line. We created here peripheral angle MSP that rests on PM, that is the diameter of the circle. Why? Because chord PM passes from point O, that is the center of the circle. Any chord that passes for the center of the circle must be the diameter. So PM is the diameter of the circle, and peripheral angle MSP rests on MP, that is the diameter of the circle, therefore it is equal to 90 degrees. We define this angle as theta, therefore this angle must be equal to 90 degrees minus theta. In the right angle FQP, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. Then we proved that the green triangle is similar to the big right angle. Why? Because those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. Those two angles, they are both equal to 90 degrees, therefore they are equal to each other. And angle theta is a common angle, so angle theta equals to itself. So we proved that those two triangles can go into each other according to angle similarity rule. And from the fact that the two triangles can go into each other, we conclude that FP over SP equals to QP over MP. FP equals to A, SP equals to 6 units according to what is given as the question. QP equals to 5 plus 6, that is 11. And MP is the diameter of the circle, that is equal to B. So we concluded and found out that A over B equals to 11, A over 6 equals to 11 over B. We cross-multiplied this equation and found out that A times B equals to 66. The area of rectangle ABCD equals to the length of the rectangle, that is AB, times the width, that is BC. AB is A and BC is B according to our definition. We just write down, found out that AB equals to 66. So in conclusion, found out that the area of rectangle ABCD equals to 66 square units. That is the result that we got in both methods. And we actually also found out that in question number 1, that the radius of the circle that is described by triangle ABC is equal to 0.6589 units in both methods. Okay, thank you very much.